Gongjie. She did her undergrad at Caltech, and then she did her PhD at Harvard. Remarkable about that, we had the same advisor, which is how we met each other, and we do actually have a paper together, believe it or not, related to what she's going to talk about. And I remember we were planning on making, having more papers, but then of course COVID hit and everything got messed up, and she got a faculty position at this other institute, which I won't mention, and now we're here in the same city. And I will say, Gongjie is not only a wonderful scientist, she's a wonderful person, and we're really thrilled to have her and very lucky. Thank you, Gongjie.
Yeah, thank you very much, Eden. So it's my great pleasure to be here and to discuss about the spin dynamics of stars and planets and how they tell us about the formation and habitability of this planetary system of other stars in our universe. So let's get started, and let us start first on the spin rotation of stars. So very interestingly, over the past hundreds of years, we know one rotation of stars very well, and it is our own sun. So it is well known from the measurements of the stellar spots back to the age of Galileo, varying the stellar rotation, the sun rotation from varying its stellar spots. We know very well that the sun is rotating in alignment with the other orbits of the planets. And looking at our solar system, it's remarkable that the planets are very well ordered and their orbits are in the same plane, and the orbits are all orbiting in the same direction, very close to the direction of the rotation of the sun. So this orderly nature motivated this nebula hypothesis developed by Planck and further modified by Laplace, telling us how the planetary systems are formed. So under this classical understanding, the whole planetary system and stars are formed under a giant molecular cloud, which collapses. And as it collapses, it conserves angular momentum, so everything is orbiting in the preferred direction of the primordial giant molecular cloud. And in this way, the stars and planets are forming the molecular cloud as it collapses. There's no inclination excitation, no orbital tilt of the planetary orbits. And then through the interaction of the planetary orbit with the disk, with the gas, with the planet interaction with the gaseous environment, the eccentricity of the elongation of the orbits get damped. So one would obtain the current solar system structure, where the planets all have near circular orbits, orbiting in the similar direction as the rotation axis of the whole star. So now, there are thousands of exoplanetary systems discovered in the past 2 decades that really revolutionize our understanding of these planetary systems. And one remarkable thing is we learned that this planetary system can be very different from the solar system planets. They can come with very different orbital structures, some of them having very eccentric, elongated orbits, and also with very careful measurements in detail about the planetary system. We can learn about the stellar spin and orbital misalignment of these planetary systems. So how is it measured? So we know for exoplanetary system, one very clever method to observe, to detect this planet is through the transiting method. So when the planet is orbiting the host star and one host planet is orbiting along a line of sight, crossing the host star is blocking an area on the surface of the star and making the whole system become dimmer. And the periodic dimming can tell us the existence of the planet. And moreover, this can also tell us about the spin misalignment of the planet. So specifically, if we just look at the whole star on its own, and the stars are rotating, so half of the star is approaching us, is blue shifted, and the other half is receding from us, red shifted. So if there's no planet orbiting around it, blocking the surface of the star, we can see the red shift and the blue shift side will be balanced. There's no Doppler shift due to the rotation of the star. However, if there's a planet orbiting in front of it, it can either block the approaching blue side shifted side or the red receding side. That will leave a velocity anomaly. And now in the case when the planetary orbit is well aligned with the stellar spin, we can see that velocity anomaly is symmetric. And when it's misaligned, we can see that velocity anomaly is asymmetric. So through this systematic asymmetry in the Doppler shift of the whole star, we can tell about the spin of the misalignment. So this is the technique. So what's the result of the exoplanet spin of the misalignment? So doing these measurements, these Joster-McLaughlin measurements for the stellar misalignment, there are so far more than 100 systems have the spin orbit misalignment measured. And interestingly, this can vary with a wide range of stellar spin obliquity or the spin orbit misalignment, up to around 180 degrees from the projected obliquity. So from the previous method to do the measurements, we can see it can tell us the projected spin orbit misalignment. And now one can also measure the line of sight inclination of the stellar spin axis, the rotational axis misalignment from the direction we're looking at the star. And putting this information together, one can get a true 3D spin orbit misalignment obliquity. And we can see still the stellar spin misalignment can go up to above even 130 degrees. Very different from the solar system where the misalignment is small, around 7 degrees. So now the question is, how come these exoplanets can have this drastically different orbital architecture, different from our solar system planets? So now, immediately after the observed puzzle, there are many theoretical mechanisms proposed to explain the origin of the spin of the misalignment. And this can roughly be divided into two categories. One is the primordial misalignment, when the system is forming in the protoplanetary disk. There's already a misalignment between the stellar spin axis and the protoplanetary disk. And this can be due to chaotic accretion of the protoplanetary disk gas onto the host star, as the host star is accreting from gas in the protoplanetary disk. This can have chaotic episodic accretion coming from different directions, and this can help tilt the stellar spin axis. This is one mechanism, and also this can be produced through the magnetic interactions of the host star with the protoplanetary disk, and can also tilt the spin axis of the host star. And it can also be due to dynamical interactions if the planetary system have a nearby stellar companion, and that can tilt the orientation of the disk. So this is in the category of primordial misaligned spin orbit misalignment.
So Gongjie, your point is that normally they should align, and then there are some mechanism to tilt the spin.
Yeah, exactly. So from the classical understanding of planetary formation, one would expect all the planetary system should have a line spin, stellar spin with a planetary orbit as they collapse in the molecular cloud. So this exoplanets actually conflicts with the classical understanding and revolutionize the understanding of this planetary formation. So now we're thinking about the ways to explain how this stellar spin axis got misaligned. And then there are two ways. One is the primordial misalignment when the planets are forming in the disk, and the disk can be tilted or the stellar spin can be tilted. And the other is the post-formation scenario. Thank you for the question. And another method is post-formation. So when the planetary system is formed in the disk, it's still aligned according to the classical picture of planetary formation. And afterwards, as the gas are down, the planet feels stronger interactions between themselves, and that can kick the planetary orbit and form this misalignment. And there are also many mechanisms supporting this post-formation scenario, including planet-planet scattering. One of these are Gongjie planets. So when the planets are forming the disk, they can migrate close to the host star in a very compact configuration. And then the gas just damp the planet eccentricity, damp the orbits. And when the gas are blown away by the stellar winds, the planets feel each other stronger, and they can have strong interactions and scatter each other and tilt their orbits. And this is a post-formation scenario, as well as circular resonances, the dynamical resonant interactions, and also through chaotic interactions, they can produce this large spin orbit misalignment. So now, there are many mechanisms proposed to explain the spin orbit misalignment. So the key question now is to see how the mechanisms fit together, what's the dominant mechanism, and how the different mechanisms work together, and what's the coherent picture of planet formation. And the key advantage now is to piece together all the observational information on different planetary systems together and see how we can explain the formation of the planetary system. And one interesting puzzling system is the planetary system that hosts very short orbital period planets. So these are typically terrestrial super-Earth planets, rocky planets in orbital periods less than 1 day. So these exotic planets showing in the extreme conditions can provide us insight on how the spin axis of planet help on the formation of this planet system. So one interesting observational constraint on these ultra-short period planets is measuring the inclination of the planetary orbit. So this can be obtained as the planet is transiting in front of the host star. So if the planet is transiting near its equator, it can leave a transit light curve different from the case where it have higher inclination. So having these transit measurements from this planetary system, one can measure the mutual inclination of the planets and see some systematic trends in the mutual inclination of multiplanetary system as a function of the planet spacing, the period ratio versus the distance of the close innermost planet. And then one cool feature is shown here, where it has been found that the mutual inclination is typically larger when the innermost planet is closer in the host star. And also, the planetary mutual inclination is larger when the period ratio is larger, so when the spacing between the planet is farther out. So what does this observational trend tell us about the formation of these planets and constraining on the primordial spin-orbital misalignment versus post-formation spin-orbital misalignment? So you can see, first of all, the dynamical migration of these planets in the case of post-formation misalignment range, where the planets interact with each other stronger and do not migrate all quietly in the disk, can naturally explain this trend. In particular, in this case, the planet will interact with each other and migrate closer to the host star, assuming they all form very far away outside the snow line in the first, and migrate closer in. And then as they migrate closer into the host star to form these ultra-short period planets, their orbit get dynamically heated, and then the mutual inclination can become larger. So this is agree with the Monte Carlo simulations, where for systems that form these ultra-short period planets, they can have larger mutual inclination. However, does this mean that this in situ migration quark formation mechanism is not compatible with the observational trend? So we look at it closer, and then we notice that for these ultra-short period planets, they feel stronger interactions with the host star, and then the stellar quadruple moment can play an important role. So in particular, when the host star is rotating, you can acquire this quadruple moment, and with this quadruple moment in the center, the planetary orbit can precess like this. And the precession rate depends on the distance of the planet to the host star. And then if you have multi-planets, the precession rate will be different, and this differential precession can enhance the mutual inclination. But meanwhile, we can also see that this depends on the planet separations, because when the planets are closely packed to each other, the planet-planet coupling become also dominant, and then the two planets will precess together around the host star in a plane. So this does not excite the mutual inclination of the planetary orbit. So putting this together, we can see that the planetary mutual inclination can naturally be enhanced if the innermost planet become closer to the host star, or when the distance spacing becomes larger, in which case the planet-planet coupling becomes weaker, and the differential precession can enhance the mutual inclination. So this is supporting the case where even when the planets are forming in the disk, do not having their orbits heated up through planet-planet interaction, it still have the chance to agree with observations, to use the mutual inclination as a constraint on the formation of this planetary system. So here is our Monte Carlo simulation result. So the left is the observed systems, And then the red is the simulated systems, assuming the stellar spin of the misalignment follows the observation with only a very small 3-degree average obliquity. So this small spin of the misalignment in the center can enhance the differential precession and allowing the planets at larger spaces to develop this large mutual inclination. And then we can see naturally when the planets are closely packed, the spacing is close to each other, the planet will precess in the same plane and then still keep the same orientation in the original photoplanetary disk. However, only when they're farther apart, the mutual inclination can be excited. So this is telling us that in both cases, where the dynamically dominated planetary formation, it can be agreeable with the observed feature where the planets migrate in through planet-planet interactions. The disk, the orbit can be dynamically heated and have large mutual inclination. And meanwhile, even when they're all forming inside disk, migrating with a quiet channel, it can also develop the same feature. So there's more to do using observation to break up the different categories of planetary formation. So this is a conclusion that is still cannot exclude the in situ and disk migration. So seemingly disappointing at this stage, but through this mechanism, understanding the spin planet stellar spin interactions with the planets, we can also actually provide detailed understanding on specific planetary systems individually. So let's look at the population statistical behavior of this planetary formation. But if we look at each individual planetary system, it can also tell us a lot about the formation history and story of some interesting observed systems, such as the case of a K2266. So this is a planetary system that have an ultra-short period planet orbiting less than 1 day around the host star. And in companion with this system comes STEEP, which is a remarkable observation of TESS, Kepler, all those transiting surveys. They are really abundant in our universe. These are systems with orbital periods within 0.5 AU within the orbit of Mercury, and they're all very compact. The planets are very close to each other, and they're all in the same plane with near circular orbits. However, for this planetary system, although they have this very common compact in the same plane quiet planetary system, it has an interesting gemstone, which is this ultra-short period planets in the center. And interesting, this ultra-short period planets is at large inclination, around 14 to 17 degrees misaligned with the outer planets within mutual inclination within 1 degree. So what is the origin of this planetary system that has the innermost planet largely tilted from the outer edge with the companion planets? So you can see that this actually put a strong constraint on the spin evolution of the host star. So when the spin of the host star is rotating very fast, the particle potential is very large. It leads to strong orbital precession, and this way it can lead to large mutual inclination in the outer region of the planetary system. So the steep planets will not be completed. However, if the J2 of the host star is very small, this planet-planet coupling will be very strong and will damp the mutual inclination of the ultra-short period planet with its companion. So still also these two cases with a very large rotation of the host star and very small rotation of the host star, and neither agree with the observed architecture of the planetary system. So it studies this detail. So typically the host stars, when they form with angular momentum conservation as it contracts from the molecular cloud, is spinning very fast, and over time with magnetic interaction with magnetic braking, the rotation rate of the stars slower down. We can see the J2 decrease. So this tells us that the planet needs to migrate to the current location at around 10 million years, which gives a reasonable J2 that keeps the outer planets in coplanar configuration, but inside the mutual inclination of the innermost planet. So this put a time constraint on the formation of the planetary system. So looking forward, we're excited about more young systems to be detected and to constrain each individual planetary system formation and put them together to better understand the coherent formation for general exoplanetary systems. Okay. Any questions before I move on to spin axis dynamics for planets? Okay, please.
So the delta I was constrained to less than about 10 degrees in most cases?
Yeah, totally. So the data of Gaussian incarnation. So this is from this plot, right? So the reason is actually also from observational biases. So this data I is measured from the impact parameter of the host star. So you can see this is measured from this transit. So for all these planets, it transit. So the star has a finite size. It can have grazing orbit touching the edge, or it has like a approximate equator. So the data I is just measuring this small range between the radius of the planet, of the host star to the semi-major axis. And that's why it's all within 10 degrees. And then it's also have a minimum bound because it also depends on the node. So they could both like transiting across the equator, but from this direction, one that direction. So you can have larger between inclination than this one. So this is actually a minimum between inclination for this planetary system. And the reason, yes.
So there is no, so you're saying it's observed to the limit that it can be observed to cause a transit.
Yeah, exactly.
For the most part. And
yes.
Statistically, does this agree with most of the exoplanet systems? And why is our solar system so weird?
Yeah, that's a very good point. So this actually is larger comparing to the multiplanetary system in general. So there's a bimodal feature for Kepler system. One is the category where the planets are having multiplanets, and the neutral incarnation is very small, within 3 degrees. And this is actually within the observational bias as studied by Sarah Bullard and many other observers. Very cleverly look at whether this is caused by observational bias. So actually, for many of the multiplanetary systems, it's very similar to the solar system, where the planetary orbits are very naturally spread within 3 degrees. And then another group, it's very wild. It's like they can have very large neutral planets and very eccentric orbit. So this one is definitely for the multiplanetary system. It's not belonging to the code dichotomy, the code calculation. So I think this is because the planets when they go very close in. So these are all the systems including ultra short period planets. So when we are having orbit periods less than 1 day, star interaction is too strong that can tilt the orbit. And when they're farther apart, it's more consistent with the distribution. Please.
I have a question. So the graphs that were produced, was this used to be language? So which programming language do you use for this?
Oh yeah, okay, good question. So I personally like to use MATLAB, but I know like new generation use Python. But yeah, some of them are using Python, and some are using MATLAB, and some of them using like different other languages, depending on the age of the researchers. Sometimes. Yeah, Fortran totally. Yeah, I still use Fortran in astronomy. Yeah, have fun with those languages. Other questions? Okay. So if not, let's move on to planetary system. So one final cool takeaway message here is one interesting thing for the formation of exoplanets so far is the category of the cold multiplanetary system. They are cold and circular. They are all alike. But for the eccentric and the misaligned system, each of the systems is eccentric and misaligned in their own ways. So it's very similar to the classic literature work where happy families are alike and these are each of the less fortunate families have its own stories. Okay, so let's move on to planetary spin dynamics. So this will also bring us closer to our own home on our Earth, on the influence of planetary spin dynamics to our everyday life. So now let's look at our own Earth. So first, we are very lucky. The Earth's spin axis is slightly misaligned, about like 23 degrees misaligned from its orbit. So as it orbits around host star standing at the north hemisphere, we can feel this very nice change of the 4 seasons of winter, fall, summer, and spring. However, not all planets are so lucky. So look at our neighbor, Mars. Although the dynamical features are very similar, but Mars' spin axis can vary from 0 to 60 degrees. And this can cause drastic differences on its surface climate. and which is supported by geological evidences. For instance, at the mid-latitude of Mars, there are glacier-like features, which is incompatible with current Mars obliquity around 20 degrees. So this supports that in the past that Mars can actually have a very large obliquity, where the pole is directly towards the sun and equator, and the mid-latitude is very cold. And the hemisphere, the atmosphere can precipitate snows and form these glacier-like features. So now the question is, the Earth and Mars dynamical features are very similar to each other, but why our Earth have a stable obliquity with very small variations, but Mars have these chaotic spin variations? So to answer that, let's take a step back and look at what are the mechanisms influencing the spin dynamics of planets. So first of all, as the Earth rotates, it has a quadrupole movement, and due to the gravitational torque from the host star, the spin axis of the planet can precess. So this is very similar to what we saw for the case of the stellar spin dynamics, but the only difference here is the planet mass is very small, so the angular momentum is also very small, comparing with the orbital angular momentum. So for the case of the planet spin axis precesses, and for the case of the sun, for these closing planets, the planet orbit precesses instead of the stellar spin precesses. So here we can see the Earth spin axis precesses. And at the same time, just with the precession, we can see the obliquity spin of the misalignment is fixed. WT is not varying with large amplitude, right? So what is causing the variation? Then we can see for the solar system, the Earth is not a single child, has many planet siblings, and the siblings can perturb the planetary orbit and make it oscillate. And now, putting this together is analogous to a precessing top on the oscillating plane. And when the spin precession rate matches with the oscillation precession frequency, it can induce spin orbit resonances. And this secular spin orbit resonances can produce large-scale obliquity variations, just like pushing a child on a swing with the same frequency. Okay, so now let's get back to our Earth. So back in 1993, last scientists co-authors investigate the case of Earth spin variations. So they did a Fourier transform on the Earth orbit and look at what are the forcing frequencies on Earth orbit. And it's plotted as modes here. Now I can calculate what is the precession frequency of Earth axis causing from the sun. And then doing this calculation, we can see the precession frequency actually is very close to the forcing frequencies. So this is telling us with the sun's torque, the Earth's spin axis should have very large obliquity variations, right? So the question is, what is missing in this picture?
Moon.
Yeah, exactly. So we're missing the moon. So now adding the moon, we can see the moon is also torquing the Earth's spin axis and making the precessing faster away from the forcing frequencies. So this actually detunes the spin of the resonances and allow the Earth to have stable obliquity. So this agrees with numerical calculations. So with the moon, starting with different initial obliquity and running for 10 million years, it's found that if it starts around 20 degrees, it's quite stable. And unstable chaotic region only occurs at higher obliquity. However, for the case without the moon, even at a lower obliquity region, we can have large variations up to 50 degrees within 10 million years. And then if allow time to go longer, it can eventually go up to 80 degrees. So this is the case without the moon, and it's telling us that we really need to appreciate the existence of the moon, which stabilizes obliquity, and we know when winter is coming, and we don't need to worry about unknown monsters coming. We don't know when winter will be here. Okay, so this is the case for our own solar system, and now there are so many exoplanetary systems discovered. So now our question is, how do we know about the spin axis dynamics of these exoplanets, and which can tell us whether it's similar to the solar system, how it influences the climate, whether it produces habitable planets. And now the question is whether it also similar to the Earth that require a large satellite to stabilize the obliquity. So this is one important factor one needs to consider among many others. Exoplanet habitability, including stellar effects, planetary dynamical effects, and planetary interior properties, combine many different frontiers together. So it's a very emerging, exciting field combining many different areas of research to better understand habitability of planets. Okay, so first we studied chapter 186F. Which is a habitable zone exoplanet slightly larger than the size of Earth, orbiting 130 days around the lower mass star. And these planets plotted here also have planetary companions perturbing its orbit. So we're interested in knowing whether this exoplanet could have large orbital variations. So similarly to the case of the Earth, we obtain a Fourier transform of the orbital variation of the planet pushed by the companion planets, which is shown here. And now we can estimate what's the precession frequency of the planet, assuming it's all Earth-like, which is the arrow shown here. So this is showing us that the precession frequency of the planet is quite different from the orbital perturbing frequencies. So this planet is likely not on spin-orbit resonances and do not have large oblique variations, different from the moonless Earth. And we can also see that even including the moon, this precession frequency will be even larger, different from the orbital precession frequency. So it's still not causing the planet to have large oblique variations without moon. So now you may wonder, so for this exoplanet, we know basically nothing about its interior structure, its composition. How confident are we on this result, right? Now we can realize something inherently different on the spectrum, outer spectrum for this exoplanet. We're comparing with the solar system, the Earth orbital spectrum. We can see it has many dominant modes, and here it only have one mode. And what is causing this? And this is because the underlying architecture of the planetary system. So for these exoplanets, the companion planets are all very far away from it. So the companion planets all act together like a massive ring perturbing the orbit of the planet. So they only have one dominant mode. And for the Earth, it's closely packed together with the other three terrestrial planets that provide this S1 to S4 modes, just strongly coupled to each other. That's why it has many more modes, and it also have the dominance of Jupiter, produce this S5 and S6 modes from Jupiter and Saturn. So for the case of the Earth, it has many dominant modes and enhanced likelihood for spinning up the resonances. And for this chapter 186F, because of the architecture properties, the other companions are very far away from the habitable zone planet and only have one dominant mode, so it requires a very highly fine-tuned configuration for spinning up the resonances to occur, even though we don't really know the inherent composition of the planet. So we can tell for large likelihood that chapter 186F will have stable obliquity. And it agrees with numerical simulations comparing the frequency analysis with simulating this spin evolution numerically. Okay, so now you may wonder, so we're looking at how the spin varies for the planets, but how does actually affect the climate on the planetary system? So back in 1997, inspired by the case of a moonless Earth, where Earth obliquity can have large variations, people back then, by Williams and Custing, thinking about what would be the climate of the Earth if it has large obliquity. So they run one-dimensional energy balance models looking at the energy from the star and then absorbed from the star and also reflected from the cloud and also thermal emission from the Earth. Equating this together, they can obtain the surface temperature of the Earth as a function of its latitude for different latitudes. So this is the obliquity is 90 degrees. So the different type of lines is at different latitude, and this x-axis is the orbital phase of the planet. So we can see when the obliquity is very high at the pole area, it will have drastic temperature variations at the pole area, where here is too hot and here is very cold, hopping around, some very different from the low obligate case. One interesting feature, takeaway message is the obliquity around 54 degrees is very important. So when obliquity is larger than this, climate zonation will be changed, meaning the equator will become icy and the pole area will become warmer, and this will come back again when we look at this. So when obliquity is very high, the equator will be warm and the pole areas will be colder. Okay, so then this is the climate variations when we only have a constant obliquity at different values. And now we can see from our simulations obliquity can vary, so we'll wonder how climate will respond as the obliquity is changing over time. So we apply this to planets around binary stars. I know many people sitting here like binary stars. So for the binary stars, the companion star can very effectively torque in the orbit of the planet. And for the case when the stellar when the planet's spin and orbit is not strongly coupled, the spin is fixed and the orbit is torqued by the companion star, it can induce very large obliquity variations. So here is the result, where the upper panel plots the eccentricity of the planet and the lower panel plots the obliquity variation of the planets. So you can see from the due to the effects of the stellar companion, obliquity can have large variations. And this can have interesting effects on the climate. So we also put it in the one-dimensional energy balance model. And you can see when the obliquity is low, around 23 degrees, this is a familiar scenario where the last panel plots the amount of ice at different latitude. So when obliquity is low, the pole area will be icy and the equator will be warm. However, when the obliquity becomes higher, the climate zonation will be reversed, and the equator will become all icy, and the pole area, the ice will be melted. However, when it goes back down, when obliquity goes back down, because the ice belt will have large thermal inertia, because it has much more massive, much more surface area, the ice will not be melted fast enough. And at that time, the pole area will also become icy because it's colder. The whole planet will very easily become a snowball. So we find these large obliquity variations can enhance the probability for the planet to undergo a snowball transition. Okay, so far we're looking at the obliquity variation of the planet, which is the spin of the misalignment. And there's another interesting aspect on the planet's spin, that is the rotation of the planet itself, which tells us the day-night cycles. And it can have interesting phenomena when we're looking at compact planetary systems. So in particular, we're looking at TRAPPIST-1 as an example. So TRAPPIST-1 is a planetary system that have 7 Earth-like planets closely orbit a very small star about very close to us, 40 light years away. So this is the so-called miniature solar system. It has a similar number of planets inside this planetary system. And very interesting, this planetary system have 3 to 4 planets residing in the habitable zone, depending on how you define habitable zone. And this planetary system is very close to us, so it allows a lot of follow-up observations to characterize the planetary systems in detail. So one cool thing about the planets in the compact system is, for a long time in the past, when people think about planets very close to a host star in compact planetary system, people will imagine the planets are all tidally locked, just the case that our moon always having one face facing us and the other face facing away from us due to strong tidal interactions. And people were studying how habitable are these tidally locked planets in compact systems. However, one is missing something, because for the compact planetary system, planet interaction is also very strong. So it's also possible that the planet can keep each other's orbit and keep the planets out of the tidally locked configuration. So to investigate this, we developed a symplectic integrator to look at the spin evolution of the planets, starting from the first principle of rigid body dynamics. And we find actually for these TRAPPIST-1 planets, F in particular, the planet-planet interaction is strong enough that it can actually keep the planets out of the tidal locking. So you do not have permanent this side and permanent that side. And what's more interesting is it can actually lead to chaotic spin evolutions. So the planet can have chaotic day-night cycles. And then for planet E, because planet E is closer in to the host star, so tidal interaction is stronger. So for planet E, the spin misalignment is always very small, so it's still very well locked in the tidal locked configuration, having nearly permanent day side and permanent night side. Okay, so now you may wonder, this sounds very exciting, we have chaotic day-night cycles. What it actually does to the climate on this planet. So we moved on and include this 3D global climate model to investigate how the chaotic spin variations affect the climate of an Earth-like planet in the habitable zone that choice E and F. And here is the result. So we look at extreme case and we tweak it a little bit here. We will assume that planet E can also have very chaotic spin variations up to 180 degrees. Sometimes it's circling around, rotating, sometimes it's tidally locked. And just turn off the tidal dissipation for planet E2. And then we look at planet E and planet F together. So in this plot, the dashed line here, and here this shows the case when planet is tidally locked, and the solid line shows the case where it have chaotic spin variations. And the y-axis shows the percentage of ice-free area. So when it's dropped to 0, the planet is becoming a snowball as a function of time. So this is very short, in a couple of 100 years, 100 Earth years. And then the result is we can see for planet F, even when have chaotic spin variations, tidally locked versus non-tidally locked, the amount of ice ocean fraction is similar. However, for planet F, we can see the planet very quickly become a snowball within 300 Earth years. And the reason also goes back similar to the case when we look at oblique variations. This is due to the ice thermal inertia of the ice. So for planet E, when it's colder, ice is more likely to be produced. So when ice is formed, it takes time for the ice to melt. But when it's quickly become chaotically daring, ice do not have enough time to melt, and the ice keeps forming, and this could change the planet F into a snowball. So the takeaway message is for planet in the outer habitable zone, when it's colder, the planet is more likely to become a snowball when it have these chaotic spin variations. So not very favorable for life that we know of. Okay, so the spin variation can also cause interesting signature on transit timing variations. So due to the time limit, I'm not going to the detail, but talk to me after the talk if you're interested in transit timing variations and characterizing planetary companion masses. Okay, so lastly, I'll also talk about the formation, go back to the formation planetary system, but now starting from the measurements on the planet spin axis tilt from the host. So far we are already impressed that we have hundreds of measurements on stellar spin orbital misalignment from the raster microscopic measurements. And we may wonder whether it's actually possible to actually constrain the misalignment of the planet itself, because planets are so small, so thin, it's very difficult to measure its property directly. But very excitingly, recently by Marta Bright in 2020, we have a first constraint about misalignment for planet mass object. So this is a system around quite young, 100 million years, around the host star, 0.4 solar masses, and planet is quite large. At a large separation, 50 AU from the host star. So they obtained a very high resolution spectrum on the planet and combined that with the astrometric measurements on the orbital evolution, optical motion of the planet to constrain the spin and orbit misalignment. And here's the result. So the black line shows the isotropic distribution on the obliquely, and then the blue line is their constraint, their observation measurements. So you can see they are slightly different, and this gives some inclination showing that this favors misalignment for the planetary system. So this is some cool constraint we can put on the planetary system. So why is this puzzling? So putting back all the other information planetary systems here, we can see for the host star, the stellar spin axis is actually quite well aligned with the planetary orbit. from the astrometric measurements of the planetary motion. However, the planet's spin axis is very largely misaligned. So what leads to the misalignment of the planet? So people, similar to what we discussed earlier in this talk, they consider secular spin of the resonances. But the challenge here is the planet is very far away from the host star at 50 AU, so the spin precession frequency is very small. So it's very unlikely to have spin of the resonances to the spin axis. So it's still not clear what is the origin of the planetary spin axis. And then we realize we can also learn from other properties of the planetary orbit, and that is the planetary orbital eccentricity is not very, very high, approach about 0.9. So I wonder whether the planet's spin axis got tilted as the orbital eccentricity got also got excited. And we look at the classical formation from planet-planet scattering, where the planetary system formed from giant molecular cloud and a macro in the protoplanetary disk in a compact configuration. And then when the gas is blown away, the planet feel each other stronger, and then it's scattered. And then this is very dominant. It can produce a large variety of planetary systems, including hot Jupiter planets very close to the host star, very hot. Warm Jupiters in a slightly larger, wider orbits, and it can also produce wide orbital planets, can explain many observational features. So I wonder whether during planet-planet scattering, when the planets obtain this large eccentricity and ending at far distances, whether the spin axis can be tilted meanwhile. So again, we adopt our rigid body integrators and look at the planet-planet scattering and evolving the spin axis of planets at the same time. Oh yeah, so it doesn't have the movie here. So sorry about that. So we can imagine these three planets all interact with each other, and the spin axis can indeed be excited. And then during the scattering, you can also see the lower mass planets will be ejected away as they are kicked around by the more massive planet. So in the end, naturally, you end up with a more massive planet, and you have a large tilt of the planetary spin axis. So this is shown here. And we wonder what is actually causing the spin axis to tilt, because even when the planets scatter with each other, the torque on the orbit is actually larger and allow the orbit to be tilted before the spin of the planet gets tilted. So we look at this evolution in detail, and then we find actually during the scattering, during the close encounter of the planets, the spin orbit resonances can still kick in, and that can lead to the spin excitation at a longer time scale, at a secular time scale, to excite the spin axis of the planet. So this can also put a constraint on the possible origin of this planetary system from planet-planet scattering based on the planetary spin measurements. Okay, and then you may wonder whether this occurs for this particular planetary system and how common it is for planetary system in general. So we did multicolor simulations on the planet-planet scattering, and then record the time when it encounters the spin of the resonances. And we can see that actually a large amount of the systems, more than 50% of them, actually have spin of the resonances and can have the planetary spin axis tilt during the scattering. That's the end of my talk, as we also reach close to the limit of the talk. So we look at the stellar spin and the planetary spin dynamics of planetary system, and look at how they can constrain both the formation and habitability of planetary system. So you can see stellar spin orbit coupling can enhance mutual inclination of these multiplanetary systems, and then planetary obliquity can influence the climate, induce snowball translations, and this can also give imprints on the scattering of these planetary systems. Okay, so I hope you enjoyed the talk.
Thank you so much, Gongjie. This is awesome. I have a quick question for you. I'll start off with questions. Venus, has the retrograde, spin, unlike any of the other planets here. In your research, have you come across something like that in your simulations? And if so, what do what in your mind actually is, caused Venus to have this weird spin?
Yeah, this is a very good question. So one interesting feature for spin of the resonances is typically only producing obliquities up to around 90 degrees. And the reason is through the spin of the resonances is resonant with the orbital precession and a spin precession. And then for planetary orbital precession, the nodal precession direction is retrograde. So they are only resonate with spin precession that's in the same direction. And then spin precession sign depends on the obliquity of the planet. So only one planet obliquity is below 90 degrees, they can naturally resonate with orbital precession that is retrograde. So for typical planetary system, just through secular planet-planet interactions in the low eccentricity, low inclination regime, it can only lead to obliquity up to 90 degrees. So for the solar system, the Venus obliquity around retrograde is mostly from the atmospheric tides, where the retrograde is a stable, is an equilibrium configuration. So this is not a result of spin of the resonances. Different from many of the other planets in the solar system, including Earth and Mars, as we mentioned, also from Saturn obliquity, from the secular spin of the resonances during its formation, and also Uranus, which could have spin of the resonances on top of the impacts to have this large obliquity of Uranus. But if you have more chaotic dynamics, you could have prograde nodal precession, and then you can have secular spin of the resonances up to retrograde, but it's not very common. General near circular near coplanar.
Super fascinating. Thank you. So, other questions? Yes, Misty.
So I think I heard you say impacts, which is how we explain an awful lot of things in our own solar system in terms of our own sideways planet Uranus, as well as lots of other features that we find, such as why do we have a moon? And so, but I didn't hear you talking about impacts in any of your simulations here. So I was wondering if there's some work on how impacts might be affecting the variety of planetary systems we're finding with exoplanets.
Yeah, totally. So here, due to the time limit, we just focus on the secular resonances, but definitely impacts also play a very important role. Like Hukash, Gongjie in UCLA studied a lot on the results of impacts on exoplanetary systems, and also Donglai, their group also studied impacts on planetary spin dynamics too. So we can see, so this definitely plays a very important role on the planet formation, and also, but this secular spin of the resonances also is very important, where they don't physically have an impact, but the dynamical orbital variations can also lead to variations. So I think these two, dynamically speaking, they are very complementary. Where the impact is also very fast, and you have a sudden change of the spin axis, and secular dynamics is very slowly over time, the resonances kick spin. So it's also some differences. And I think in the end outcome, if in the future one can concentrate more on the size and the mass of this planet's impact, and the secular resonances will also give different results, where the impact where the envelope may be lost for the planets, and the secular resonances, the planet's more impact. So there's lots more to be useful. So thank you.
Great question. All right, Misty.
So, if I understand correctly, precession is a result of the general theory of relativity. You don't see precession in Newtonian mechanics.
Oh, okay. So precession occurs in any potential that's not point mass. So it's true that it occurs in general relativity precession, where the pericentric direction changes. But it also occurs if you have a quadruple moment, where the central source essentially is not a point mass. Well, if you have a quadruple potential, the orbit will also precess.
Even if you use Newtonian mechanics.
Even if you use Newtonian mechanics, really from like multiple expansion.
So do resonances also are resonances also observed in Newtonian mechanics, or do you need?
No. So these are all Newtonian that we discussed. So we included GR, but the dominant resonances here is Newtonian resonances. So like when you have multiple expansion, you can have this beyond point mass potential, can have precession, and also if you have a companion, also have precession. So these are all Newtonian results. Yes.
Pete.
Did you find any examples in your calculations of this where a planet gets kicked out of its system?
Oh yeah, this happens a lot. If the animation works, you can see that we started with 3, and then 2 of them got kicked out. And actually, in our universe, I'm sure many of the experts sitting here also see like there are many free floating planets that are wandering without a host star. So those are likely like planets ejected from their home planet for like wandering planets.
Did you do any investigation into geoplanet systems with larger moons and how maybe, or how the angular momentum of the whole system might process?
Yeah,
related to
totally.
the,
That's a very exciting direction of studies. Actually, my postdoc Billy Claus and I will study this dynamics of the moons a lot. And one cool thing you may wonder actually for our own solar system, why we have a moon, Mars have a moon, and then the other planets have a moon, but Mercury and Venus, why don't they have a moon? So this was studied back in 1980s by Mark Reed, interestingly he later on does not study planetary dynamics. Yeah, so they actually had a study on Venus moon, and it's interesting for this three-body system, the star, planet, and the moon. There's no equilibrium, so the moon will either collide onto the planet or escape from the Hill radius of the planet. And then for the Venus, it's closer in and time scale is shorter, so it does not have a moon. Even if it has a moon to begin with, it will be lost. And then for our moon, it's on the way to escape from us, but that takes a long time, so we don't worry about it.
Gongjie, thanks for the excellent talk. So, but after your talk, I become a bit more pessimistic to find an alien because you showed that there's a lot of subtlety for the planet to be inhabitable. So, but how hard are we going to be able to find an inhabitable planet besides the Earth?
Yeah, I think it's very, it's a great question. And there are many things to consider. And I feel like the most challenging thing is now we're not really sure what would be the signature that unambiguously tell us that the existence of life on other planetary systems. So it's very exciting with especially with the GWST observation of the planetary atmospheres. We can try to find biosignatures. And now there are many proposing elements that can study when the chemicals can exist in non-equilibrium conditions that may suggest something that happened very recent. And those could be really cool, exciting signatures that give high potential for saying it could be life forms on the exoplanetary system. And also within the solar system, there are many studies on Europa and on Enceladus, and to see whether there are signatures of life even within the solar system. So there, it is challenging, but we're taking steps over there.
Have faith.
Yeah, yeah, and the life forms, they can be very robust. Right? So even we had snowball on our Earth, and we somehow survived. So it's like challenging for life that we know of, and there could be like life forms in extreme conditions where people are also studying Earth, look at extreme condition life forms, and to learn more about.
I mean, bacteria can survive in space. You know, just space without any insulation. It's amazing, yeah. And tardigrades as well.
Bacteria.
What's that?
But I cannot talk to bacteria.
That's true.
I just say that snowball is fun. Like
It could be fun, yes.
Okay.
But if it's on the snowball for too long, it may be a problem. But I'm not an expert in that area, so I won't say too much on it. So, but yeah.
Do you think the Earth's spin has some effect on melting ice?
On what?
Melting ice?
Oh yeah, totally. So the Earth had undergone this snowball effect. They have these glacier cycles, and these glacier cycles is very well correlated with the Milankovitch cycles of Earth. And the Milankovitch cycles is the oscillation of the Earth, the notation of the Earth spin axis together with eccentricity variations. So eccentricity and spin all together influence the amount of insolation that we have at a given latitude on the surface of the Earth. And then checking back, it also agrees with the isotope measurements with deep sea ocean ice that with a few degree temperature shift from the spin and eccentricity variations from the Milankovitch cycles that gives us these glacier cycles that ice melt and ice snowball face of the Earth.
So the global warming will affect our spin?
The vice versa, it's possible. So I don't know. So the global warming will be.
We'll find out.
We'll find out.
I'm on your
Yeah, sorry. One of you missed a slide about if you had any like proper like
statistical percentages of planets that we now know, like it's around 6,000 planets. How many of them, if we can find using the RV Doppler shift and see if they're misaligned or not, how many of them do misalign? And if that's, what does it look like as a function of planet mass and as a function of stellar mass?
Yeah, that's a very good question. So if we go back, and we can see very interesting dependence on the stellar mass first of all. So I don't. Let's see if I have a backup slides. So I was talking with Russell about this before our talk. So essentially, for the cool stars, the lower mass stars, the stellar spin orbit misalignment is typically very small. It's all very well aligned. But for stars with larger masses, higher temperatures beyond around 6,000 Kelvin, and you can see the misalignment is more wild and has larger misalignment range. And there are many mechanisms. You can see the theories are very good at coming up with all different mechanisms. There are many mechanisms coming up to explain this, including for the lower mass stars, they have convective envelope, and that may induce stronger tides. And stronger tides can realign the planetary orbit with the stellar spin axis. And it's not the case for the higher mass stars, hotter stars, where they have a radiative envelope and has a weaker, so it's misaligned. So this is under assumption that they're misaligned in the beginning and then it got realigned afterwards. And there are also theories proposing that the lower mass have stronger magnetic interactions that can keep the stellar spin axis being aligned with the disk in the beginning, and then when the hotter stars has a weak magnetic and more wildly misaligned. So you can see the cyan color is the black color is the Saturns, and then the other colors are Jupiters. So you can see roughly similar that the Saturn color looks like this. And another thing is for the Neptunes, which is not shown here. For the Neptunes, recently it's been found that Neptunes, many of them are interestingly clustered around 90 degrees. And I need to be very cautious speaking this, because some people think it's clustered around 90 degrees, some people think it's not statistically significant. And so there's still arguments going on. So it's possibly have some dependence on the planet mass too. And also it has an interesting dependence on the distance. So farther away, you can see it can have larger misalignment, especially if you're focusing on the cool stars. At farther distances, they can have larger misalignment, and closer in, they can be more aligned. Please?
Yeah, so my understanding of biological life and organisms is it requires locally for entropy to kind of decrease locally. Right. So, which constrains the models of what can be, and how relating this back to spin precession of a planet, and what allows for basically this for these local entropy decreases for life to arise or occur on that planet. My question I'm getting at is in terms of, because there's lots of ways. One of the key hallmarks of this whole thing is how does the living organism undergo metabolism? How can it get its own energy? Right, but many mechanisms upon which that do that. There's like lithotropes and extremophiles and so on. In terms of upper and lower bounds, how does in terms of the precession of spin on these planets, what can the constraints upon which it is possible for a life to exist in relation to the planetary precessions that you're speaking about? How do those things become? How do you use one parameter? I'm going to try to relate the sets of parameters together.
Yeah, so we can see for planetary habitability, that's a very good question. So essentially looking at all the different factors concerning planetary habitability. You have the entropy, and then you also have the spin variations, and then you also have orbital dynamics, and then you also have galactic influences, and then for the planet itself, it has the interior, atmosphere, surface, etc. So I think now is the stage to better understand each of the elements and put them together all together. So I think that's the current stage.
I'll also add that there's a lot of evidence without a moon, in fact, quite a large moon, that life may or may not form. Nobody knows the answer, but there is a lot of research into that. Great. Other questions? If not, Gongjie will be available if anybody has any private questions you want to say or whatnot. And let's thank our speaker for one.